Hi everyone, this is a follow-up video to my last one, which involved finding the inverse matrix of a 2 by 2 using adjoined matrices, okay? So what we're going to do in this video is extend the concept a little bit more. Not extend the concept really, but extend the mechanics of it to a 3 by 3 matrix, because we often deal with linear algebra with 2 by 2 and 3 by 3 systems of equations, and after we move beyond those types of systems, we typically move to computer-based solving methods or even finding inverses. So given a 3 by 3 matrix, let's talk about how we could do the same kind of idea to find the inverse of a 3 by 3, okay? Once again, recall that an inverse is anything when it operates with its original here, we end up with what we refer to as the identity. And actually with matrix math, we refer to that identity as the matrix I of order n. But this is a square matrix, okay? And so we say anything that has an inverse with matrices is itself a square matrix, and its inverse must, if it exists, be unique, okay? Such that A times A inverse is the identity, or A inverse times A inverse times A is also the same identity, okay? So that being said, let's go back over here and we say we already have a matrix A. It's a 3 by 3. We're going to let it be this square matrix right here. And what we're going to do is create this adjoined matrix. So again, you'll see that we have the original matrix over here on the left. We just kind of draw on this partition here, and we say what we'll put on the right here is the identity matrix, which recall is always a square matrix with ones down the main diagonal and zeros elsewhere. But our major intent here is to using the 3 elementary row operations, turn the matrix on the left here into the identity matrix, and whilst operating on this, we'll find that we're actually turning this matrix on the right here into the inverse of the original matrix. So, okay, let's go ahead and get started. Turning this into the identity matrix, recall that we want a 1 in the top left entry here, which we're kind of lucky. Yes, we already have a 1, and not maybe lucky, kind of generated this one, such that it'd be a nice example. But what we're going to do now that we have a 1 on the main diagonal here, a leading 1, we're going to make everything below it into 0 by using our EROs. So two different operations we're going to carry out here with the same matrix. Let's just say, of course we're doing it with the same matrix, but we're going to do these moves simultaneously. So what we can do is we want to eliminate this 1 here and this positive 6 here. What we'll do is we'll take this top 1 times negative 1 and add it to this 1, since that will turn it into 0. So in other words, we're going to multiply the entire first row times negative 1. So negative 1 times R1. We're going to add that to row 2. At the same time, we're going to take negative 6 times the first row here and add that to the third row, because a negative 6 times a positive 1 is a negative 6, and adding that to a positive 6 would produce a 0 down here, which is what we want. So we're going to take negative 6 times R1. We're going to add that to row 3, if you can read that. Okay, so that being said, moving right along, let's go ahead and rewrite our new matrix here, and it's kind of a big matrix. But anyways, what you'll see is this. The very, very first row, of course, the row you scalar multiplied by a scalar does not itself change. So that's itself. But we said we took negative 1 times the entire first row and added it to the entire second row. So negative 1 times 1 is negative 1. But when we add it to this positive 1, this becomes 0, as we intended to happen. But negative 1 times this negative 1 here is positive 1, and positive 1 times 0 is, of course, 1. And then negative 1 times 0 is 0, and, of course, 0 times plus anything is itself. So it is itself, so this needs to stay negative 1. Apologize. And then we also say this, okay, so negative 1 times positive 1 here is negative 1, plus 0 is negative 1. 0 times anything is 0, so 0 plus anything is itself, so those are just going to stay the same. Now moving down to the third row, we had intended to take the first row times negative 6 and add it to the third row with the intent of making this a 0, which it does. Moving on though, we say negative 1 times negative 6 is positive 6, and positive 6, of course, plus this negative 2 is 4. And we say anything times 0 is, of course, 0. And 0 plus anything is itself, so negative 3. Kind of convenient to not have to think about that if you think about it. Kind of an oxymoron there. But anyways, okay, so negative 6 times positive 1 is negative 6, plus 0 is negative 6, and these are 0, so that's nice. These will maintain themselves. Okay, so now that we have this new matrix, you'll see that in this entire first column, we've got what we want, a 1, a leading 1 on the main diagonal there, and then everything below it's 0. So let's talk about the next entry on the main diagonal, which will be this here. If this wasn't a 1 now, we would want to scalar multiply such that it became a 1. Becomes a 1, but it already is a 1, so that's the nice thing about it. We need to make everything above and below it into 0. So what we'll do is we'll add the second row, R2, we'll add that to the first row, essentially canceling this guy right here out. And then we'll take this 1 times -4 and add it to the third row. So -4 times row 2, and we'll add that to the third row. And that'll make these essentially disappear. So let's go ahead and move on. We're going to rewrite our matrix here. Again, a very, very large matrix. You're going to find that it's actually, you'll really appreciate using computer-aided devices when you find inverse matrices. But the second row maintains itself because all we did was scalar multiply and add it. But we did add it to the first row, so 0 plus 1 is 1. 1 plus -1 is our 0. -1 plus 0 is -1. -1 plus 1 is 0. 1 plus 0 is 1. And then 0 plus 0 is, of course, 0. Now, the thinker, not very much so, but we have to think about it. But -4 times row 2. So -4 times 0 is 0. And 0 plus anything is 0. So there's our 0 there. -4 times a +1 is -4, plus this +4 is our 0 we desired, and then -4 times -3 is 12. Pardon me. -4 times -1 is 4, and 4 plus -3 is +1. Moving on, -4 times -1 is 4, and 4 plus -6 is 2. -4 times 1 is -4, and -4 plus 0 is -4, and then last but not least, -4 times 0 does not matter because it's going to be 0, and 0 plus 1 is 1. Okay, so the very, very last thing we need to do here is make sure that this last thing on the main diagonal is a 1, and what do you know, it's already a 1. We just need to make everything above and below it a 0, which in this case is just above. And the nice thing about this example is I can just now add the third row to the second row and the first row because +1 plus these two -1s respectively will make them zeros. So we're going to say this, we're going to take row 3 plus row 2, and we're also going to take row 3 plus row 1. And since all we're doing is adding row 3, the cool thing about it is, of course, it maintains itself. So 2, -4, 1. So here we go. Okay, so 0 plus 0, row 3 plus row 2. There we go. We have a 0 there. 0 plus 1 is 1. And then 1 plus -1 is 0. It's over here that we care about. So we say 2 plus -1 is 1. -4 plus 1 is -3. And then 1 plus 0 is of course, 1. Now adding the third row to the first row, 0 plus 1 is 1, 0 plus 0 is 0, 1 plus -1 is our 0 we wanted. So now you'll notice we have the identity matrix over here on the left. And then over on the right here we have 2 plus 0 is 2, -4 plus 1 is -3, and then 1 plus 0 is 1. Now I'm probably running out of time, so for the sake of time I will tell you this. We have identified the inverse of matrix A. I would say at this point, though, it would be best if you took matrix A times A inverse just to show that you do get this identity matrix. Enjoy.